Math 287, Cuesta College. I'm Joe Vasta, and we are going to do section 11.2, series solutions about an ordinary point. And how we're going to do this is we are not going to put problems like this on the next exam. They will come, you'll get one problem that will be, it's a take-home quiz, but isn't everything take-home? And it will be something you just turn in individually, you know, apart from exam 5. And it will put a due date on there and all that. And I'll give you instructions when I send you the PDF of this take-home problem. The reason I'm doing it that way is because this take-home problem, series solutions, these problems are going to be a little more intense than anything you've had in this class. And all because of algebra. And it just takes a long time to do a problem. And so that's why we're going to do that. We do have to cover series solutions. There's a whole chapter on it. 11.1 is some sort of review, and there's other things. We have an ordinary point, we have singular point. We can spend a month doing chapter 11. Maybe I exaggerated. Okay, we can spend 3.5 weeks doing chapter 11. We're just going to do this section, and this will cover what we need to cover. So most of this lecture will be on PowerPoint. So I will transition to that after I do a few things with writing. I want to solve this equation here. This is a differential equation. It's first order. The highest derivative is the first derivative. And I'm going to solve for dy dx. This equals 2xy. We can see that this first order differential equation is separable. So I'm going to separate this. I'm going to write this as dy over y equals 2x dx. The next thing I want to do is I want to integrate both sides with respect to those letters there, x and y. And on the left-hand side, I end up getting ln absolute value y. On the right-hand side, I end up getting x squared, and then here's the c. I'm going to exponentiate both sides, so e to that equals e to that. On the left-hand side, this one right here goes pop. You end up getting the absolute value y equals e to the x squared times e to the c being another constant. So I have the absolute value of y equals c e to the x squared. That's just the different c than e to the c, and then this c is going to absorb the absolute value. So I end up getting y equals c e to the x squared power. So you might be wondering, what does this have to do with series solutions? Maybe it has nothing to do with series solutions. But now I'm going to frighten a lot of you and ask you to recall this fact about e to the x. E to the x can actually be written as an infinite series from n equals 0 to infinity, x to the n all over n factorial. So there it is. And so we can replace this. So, like, we're looking at this right here. And so I'm going to replace the x with an x squared. So watch this. E to the x squared equals summation from 0 to infinity. This is going to be x to the n, but it's going to be x squared to the n. This is all over n factorial. Okay, so that could really just be x to the 2n power, 2 times n. And so this solution, though we normally wouldn't do this, but we want to illustrate a point. This solution equals, so we have y equals constant times this critter right here. from 0 to infinity, just like a math teacher, to make something that was simple into something more complicated. And we have that right there. Now, on a problem like this, we'd probably prefer this solution right here, but we're just trying to illustrate the point that you can have a differential equation where its solution can be written as a series, infinite series. Now, on this one, it didn't have to be the case, but there are other differential equations where you cannot solve it nicely in any technique except by series solutions. Just like there are some integrals like e to the x squared that you wouldn't be able to integrate without going into power series. So these guys right here, if you remember this power series here, we know that this converges for all real values of x. And so this right here also converges for all real values of x. But knowing the solution in advance, we were able to find the power series solution of the differential equations. Now let's find the power series solution directly. I'm going to do this differential equation using power series techniques. And we're going to have a lot more work. We're just going to go ahead and show you how it's done. Lots of summation notation, and we're going to get to this. That will be problem number 1. To show you the technique in problem number 2, we're going to switch something around and do a differential equation that we cannot solve. Using the same techniques, we will get a solution. So the rest of this lecture will be PowerPoint. Okay, so we have the differential equation that we solved by separation, and we're going to look at some power series techniques. And the first thing that we want to do is realize that our solution can be written as a power series right here. Summation 0 to infinity an x to the n. Now when we write that, those are centered at x equals 0, okay? Because it's this right here is an x minus 0 inside parentheses to the nth power. And that we'll talk about that at the very end. Okay, I'm going to assume that this is a solution to the differential equation. And what I want to do is plug that solution into the differential equation here. Now in order to do that, I have to take its derivative. I'm taking the derivative with respect to n, no, did I say n? To x. And so I'm going to use the power rule here. This is going to become an x to the n minus 1, and that n is going to jump out in front. And so I have that right there. So there's the derivative. So we have this down here. Now before I plug those guys into the differential equation, I want to note where the derivative starts at. It starts at n equals 0. Now when I put n equals 0 into that series, that gives me the first term of 0, so I really don't need n equals 0, do I? So I'm just going to bump that up to n equals 1. Now I'm ready to plug these puppies here into this differential equation. Everywhere there's a y prime and a y, they're going to get replaced, and this differential equation is going to get a little bit more complicated. So there it is. So it wasn't anything big. I just plugged those in there. And what I want to do next is I want to go ahead and bring this x into the summation. And in fact, I'll bring the 2x in there and keep the negative there. So when I bring that x in there, this is going to join with this x, and it's going to become x to the n plus 1. So I left this guy alone over here, the one I'm pointing to, and I went ahead and did what I said I would do. Okay, now my next goal is look at these, and I'll do this with every single problem. I want this to say x to the n, and I would like this to say x to the n as well, but it doesn't say that. They say different things. So in order for this to get so it says x to the n, I have to re-index. Some of you might have remembered re-indexing your summation. And I want to replace all the n's. And there are 1, 2, 3, 4 occurrences of n's here. Actually 5 if you say n goes to infinity. I'm going to replace those n's with something that would put just an n up there. So I'm going to replace that n that you see the red circle near. I'm going to replace that with an n plus 1. And that would make it, so it says x to the n plus 1 minus 1, which would just then give me x to the n. Of course, this would be n plus 1 right there. That would be n plus 1. This would be n plus 1 equals 1. So n would start off at 0 then. And then this would say n goes to infinity. Well, n plus 1 goes to infinity is the same as n going to infinity. So that will be written there. Now over here, this popped up. I didn't realize it was going to pop up at the same time. I want to replace all my n's with n minus 1s because you'll see you'll have an x to the n there. So let me go ahead and show you what I get for the results. I get for the results what I said. Look, all the n's. So this n plus 1 this n got replaced with an n plus 1. I have n plus 1 equals 1, n equals 0. Then there's an n plus 1, a to the n plus 1, x to the n. And then the same thing over here, all my n's get replaced with n minus 1s. This n gets replaced with an n minus 1 on this one, so n minus 1 equals 0, so n equals 1. And we have 2a sub n minus 1, x to the n. That's exactly what I wanted. So first get x to the n's there. Next, I want both of those summations to start at the same number, and they do not start at the same number. Now, sometimes what I'll do is I'll try to take this one back and say n equals 0. But if I do that, I have 2a sub negative 1, and we don't want an a sub negative 1, so I can't take this one back to 0. What I'm going to do is if I put 0 in this one, I'm going to get 1a0 plus 1, so 1a1 x to the 0. So I'm going to plug 0 into this and write that out in front of the summation, and then that summation that is above that red dot will start at 1. And so that's what happens. So now I have not only the x to the n's there, but both of my summations start at n equals 1. Okay, so this is the result. I don't have any more room on this PowerPoint, so I'm going to, on this part, so I'm going to go to the next page. So this is exactly what I had written up. It was sticking this guy into the differential equation. I have the xn's there. They both start at 1. So the reason I did that is so I can put both of those summations together and factor out an x sub n to the right. And that's what I do. So I put both of those together, and this a1 has to just stand out there now. This x to the n got factored out there, and now I have an expression in there. Now, this on the left-hand side of this equation is a polynomial that has infinitely many terms. The constant on that polynomial is just a1. So a1 is going to equal 0. The next term of the polynomial is an x term, x to the 1, and it will have this in there. That coefficient is going to equal, the right-hand side, it's going to equal 0, because you have a 0x over there. And then the x squared coefficient, which is really just this again, will equal 0. So my next step is I have a1 equals 0 and this coefficient equaling 0. Okay, on this one I know a1 is 0 and I'm happy with that. On this one I want to solve for the one with the greatest index, which is the a sub n plus 1. So I'll do a little algebra and solve for a sub n plus 1. And I end up getting a sub n plus 1 equals 2, a sub n minus 1 over n plus 1. And so that is what I have. I know this is quite a lengthy process, but just hang in there because we're not done yet. Okay, so I'm run out of room on this page, so I'm going to put these results in boxes on the next page, up in the top left corner. So here it goes. So I'm going to go ahead and throw these on in the top left corner along with this here. Okay, so that's what I have. So now what I want to do is, I have a sub 1. I know this solves the differential equation, and really the whole goal of this whole problem is to find out patterns for a sub n. In order to do that, we need to put 1 into this formula. Okay, we're not going to put 0 in because it said n equals 1 with these formulas. That, if you look back at the last page, n started at 1. So I'm going to go ahead and put 1 into this, and I end up getting this guy right here. Now, actually, I ended up getting all of them. If I put 1 into the formula, I get this. And I put 2 into the formula. I kind of put the 2 over here. I end up getting a sub 2 plus 1 equals 2a, 2 minus 1. That's a1, and then we have 2 plus 1. And I kept it all written out. I put 3 into the formula, and 4, and 5, and 6, and 7. And you're like, well, how far do we go? You go as far as you need to go. Okay, we're going to look for some patterns. That's what we plan on doing. Okay, let's take a look at this. A sub 2 is 2a0 all over 1 plus 1, which is just a sub 0, or a naught. Now I'm going to go ahead and look at this one over here. Since a1 is 0, we see that a3 is also going to be 0. We continue. Now I should have done the one over here, but I can see that a5, because it has an a3 in it, and a3 was 0, a5 is going to be 0. And take a guess about a7. It's also going to be 0. So it looks like my a sub odd will end up giving me 0. Now we're going to go ahead and take a look at my a sub evens. So a sub 4, here's the formula. I have 2a2 over 4, or a naught over 2. Okay, now I'm going to go ahead and see what this one gives me. I'm going to replace the a4 with a naught over 2. So see how I'm putting this? I'm going to put that right there. And when I do, I end up getting, well, first of all, this is a4 over 3 because it's 2 over 6. And then I replace the a4 with an a naught over 2. So this is going to be a naught over 6. I'm going to do the same thing down here, and I'm going to keep going until I see the pattern. And so this is really 2 on the top, 8 on the bottom, so that's 1 over 4. And then replace the a6 with a naught over 6. And so I have 6 times 4 on the bottom, so that's a naught over 24. So we have to ask ourselves this question: do we see a pattern with the evens? And if you don't see the pattern, it's time to drop the class. Like a sub 3 is 0, oh, a sub 1 is 0, a sub 3 is 0, a sub 5 is 0, a sub 7 is 0, a sub 9 is 0. But this is the one where it's really, maybe you have to look hard on this one. Do you see a pattern? You see that all the terms have an a naught on the top, and on the bottom there's really a 1 there. Where have you seen the numbers 1, 2, 6, 24? Now, if you don't know the answer to that, you might want to go ahead and write n equals 9 and plug it in there and then see what number you get on the bottom. I believe you'll get 120. And so maybe when you're doing these, we want to get rid of this n equals 1, 3, 5, 7. We don't want to write those after we see the pattern. And so what I'm going to do is I'm going to say that a sub 2n, so that's these guys right here. This is a sub 2n, those are evens. They will always have an a naught on the top, and you may have already noticed that those are n factorials. This is for n greater than or equal to 1. And let's see if this actually works. If I put a 1 into this formula, then I have a2 equals a naught over 1 factorial, or just a naught. if I put 2 into this formula, then I have A4 equals A naught over 2 factorial. I put 3 into this formula, I have A6 equals A naught over 3 factorial. 4 is A naught over 4 factorial. This formula seems to work. Now the deal is when you're doing your homework, you might want to cross out all the n equals up here because this is going to kind of be a different indexing. And if anything, if I was a good teacher, I would have probably used an M here instead of an N or something. But this is good. I mean, a lot of teachers will do it the way I'm doing it. Now, can we find a pattern for A sub 2n plus 1? Well, yes, that one's pretty simple. It would be 0. And so for a lot of you, this part of the problem where you're trying to find the patterns for these two subsequences, that's going to be the hardest part. Okay. So now let's go back and put the results at the top. So I have this right here, and this right here, and I do have to remember to stop talking when it's transitioning because it mutes it. So I won't go back and fix the other ones. Hopefully I wasn't talking too much. That was our result. The thing that we wanted to solve the differential equation, this power series, is right here. And because this is broken into evens and odds, we are going to have to break this into evens and odds. How do I do that? Well, by putting 2n there and 2n there. So those are my evens. And then putting a sub 2n plus 1 there and a 2n plus 1 there. Those are my odds. And as you see, if you put 0, 1, and 2, you'll have a sub 0 here, and then 0 would be a sub 1, and then 1 would be a sub 2, and then you pick up the a sub 3. So this partitioned off the infinite series into the evens and the odds. For this one right here, we see it's 0. So I'll write a plus 0 for one step. And then this one right here, our formula starts working legitimately at n equals 1. So I'm going to have to write out the first term. A sub 0 is, n equals 0 is a sub 0 x to the 0. So it's just a sub 0. So let's go ahead and write that out. Okay, so the next part of this problem that I want to do is I want to replace, this is what I was working really hard to do, replace this a sub 2n with the formula you see right there. So that's what I'll do. That's all I did was replace it. The 0 went away. And then notice that both of these terms, there's actually infinitely many terms, but let me just be a little abusive and call this one term and this another term. Both of those terms have an a naught in common. So I'm going to factor that out front. And notice that if you were to start this at 0, let's just think about it. Like if there was a 0 here, n equals 0, this would say x to the 0 over 0 factorial. 0 factorial is 1, and x to the 0 is 1. So if you had an n equals 0, it would display 1 for the first term, which is exactly what we have over here. So what I'm going to go ahead and absorb this 1 into the summation by starting the summation at 0. And there is my result. Now, if you noticed what I did in class, there is no class, what I did at the beginning, I went ahead and solved this differential equation by separation, and then I went ahead and replaced the e to the x with its power series, and I ended up writing something like this, except instead of a naught, there was a c. So I had constant times exactly what you see here. And so this completes problem number 1, solving this using power series. And in your homework, they're going to have you do ones that you can't do by separation. And so I am going to show you the next problem. So I'll pause the talking here. There's the next problem. And it looks like our first problem, except our first problem just had a y prime there. So if we change this to y double prime, we get a differential equation, doesn't have constant coefficients. We cannot really solve this differential equation with any of the techniques that we know. So what we're going to do, and we're going to spend the rest of this PowerPoint, I believe it's the rest of this PowerPoint doing this problem, is we are going to solve this using power series. And we're going to start off this problem like we started off the other problem, where we say the solution is going to look like this. Y equals summation a sub n x to the n. So, wow, how are we going to do this? We definitely need infinite series to do this problem. So the next thing I'm going to do is take its derivative, just like I did, because I want to plug this into the differential equation. The unfortunate part is we actually have to take two derivatives because we have a y double prime there. So the first derivative is that we're taking the derivative with respect to x, and we can readjust the n equals 0, because just like the last problem, we can change that to n equals 1, because 0 just gives me a 0 term. And now I'm going to go ahead and take the derivative of that with respect to x. So I'm going to have an x to the n minus 2. It's going to look like that. And if you put 1 into this, you're going to 0 it out. So I can just start this summation at 2. Okay, so hopefully you're sitting down or you're holding on to something, because we're going to plug y and y double prime into the differential equations. It's going to get a little nasty algebraically, but you picked technical majors, so you better pretend to like this. Here it goes. Wow. There's the y double prime right there. There's the minus 2x that you see right there, and then there's y. Still looks pretty innocent. What we want to do is we want to bring this 2x inside. So if there's any x's right outside the summations, to the left of the summation, you want to bring them in. That's your first step. That's what we did in the other problem. So when I bring it in, I have the 2 there, and then this changes to an x to the n plus 1. So we might try to remember, what did I do in the other problem? I wanted to change those so they say x to the n. So this one needs some re-indexing. I'm going to replace all the n's in this expression, including the summation. I'm going to replace all those n's with n plus 2's, because that will, and that exponent will give me an x to the n then. And I'm going to replace all the n's in this summation. Well, shouldn't be circling that. In this summation with an n minus 1, and that will give me an x to the n. So here it goes. And what we end up getting, so look at this. So this n here became an n plus 2, and then this was n plus 2 minus 1, and then there was an n plus 2, and then that actually became the x to the n, which I wanted. This n got replaced with an n plus 2, n plus 2 equals 2, n equals 0, n plus 2 approaches infinity. I can subtract 2, infinity minus 2 is still infinity. The same sort of deal happens with this guy right here when you replace all those n's with n minus 1's. You can verify that. Okay, the next step that I want is I have the x to the n's there. I want to start these at the same number. If I pull this back to n equals 0, and sometimes that will work, and it will give me a 0 term there, and I could get away with that, but it's not going to give me a 0 term. It will give me 2a sub, wait, what am I, I'm seeing if I can put an n equals 0, and it will give me 2a sub n, negative 1, and then that doesn't make sense. So we have to actually write out the first term of this series here by plugging n equals 0 in. So I'll get a 2 times 1, a sub 2 x to the 0. So that's 2a2. I'll pull that out, and then that summation that is right above the red dot will start at 1. And that's all I did, was write out the first term of this, which is this, and then we have that. So you can only imagine what's going to happen now on the next, well, I'm going to rewrite this, maybe because we've run out of room. So I've rewritten this. That's exactly what we had at the bottom of the last slide. Here's the solution. And what I want to do is put those summations together. And not only I'll be putting them together, and I'll also be factoring x to the n to the right when I put them together. It's going to look like that. Okay, so here's my constant. I mean, this is a polynomial that has infinitely many terms, and this constant here, 2a2, equals 0, and so will this. This is the coefficient in front of each of the x's. That will also equal 0 because there is a 0 on the right-hand side. So, man, if we were in class, I would say, okay, I'll solve for a2 here, and you guys solve for a sub n plus 2 there, and it wouldn't even be funny. Is there anything that's funny anymore during this pandemic? No, you try to joke around, people don't laugh anymore. It's all sad. You're wearing your mask. I could be wearing a mask right now. So a2 equals 0, and then a sub n plus 2 equals a bunch of crap. And there it is. Okay, so you can actually verify that. We've run out of room on this slide, so we are going to go to the next slide. We're going to write these things right here that we just had. We're going to write those in the bottom right-hand corner along with this right here, just to remind us that that is the solution. And the whole thing that we're doing is we're trying to find out what a sub n is. There they are. And I'm going to stick n equals 1 into this formula. Remember, that's where it begins. And n equals 2 and 3 and 4 and 5 and 6 and 7 and 8. And you go as far as you can go until you see the pattern. This PowerPoint slide right here, well, this one and perhaps the next one might be the most complicated part of these problems, is finding a pattern. So there's all my n's, and I'm going to stick those n's, n equals 1 into this formula, n equals 2 into the formula, and this time I'm going to keep things all expanded out. I'm not going to, like if I see a 4 times 3, I'm not going to multiply that and say, oh, that's a 12. So this one, like for instance, I plug n equals 1 in here, and I end up getting 2a naught 3 times 2. The next one, I have a 4 times 3. And we'll continue. This one right here is 2a2 5 times 4. And so I'm just going to go ahead and plug them away just like this. And you can see, if you actually write out 8 of them or 9 or 10 of them, you see that they're really pretty simple to write out. You see the pattern and you're adjusting each time you see the next n. Okay, now, what do we know about one of these? We know that a2 equals 0. And so that's going to make a5 equals 0. And a5 equals 0 is going to force a8 to equal 0. And I don't think that's going to be the next thing. It won't let me go back. So we'll come and put a8 equals 0 after this. So what happened over here? Well, the a3 gets replaced with this right here, 2a naught 3 times 2. And so that's why this a3 disappeared. You see an a naught, there's the 2, now it's 2 squared because there was that 2, and you have 6, 5, 3, 2. I'm going to do the same thing over here. I'm going to replace the a4 with that, and so I'm going to get a 2 squared on the top and a 7, 6, 4, 3 on the bottom. And then there's an a1. And then here's the one I was really wanting to have, is a9. a9 is going to, or a8. a8 is going to be 0 because those ones are 0. So before I continue, I want you to realize that we have not evens and odds like we did in the last problem, but we have 3 subsequences. We have multiples of 3, a3, a6, a9. So we have to figure out some pattern for those. And then we have, so we would call that the 3n's. And then you have the 3n plus 1's. See, 4 is a 3n plus 1, and then 7 and 10. We have to find out a pattern for those. And then we have the 3n plus 2's, which would be, I'm not looking up at those n's, I'm looking at this. So a5 is 3n plus 2. 3 times 1 plus 2, and then this is 3 times 2 plus 2. And then the next one would be 8, 9, 10, 11. And we know that a11 is going to equal 0 as well. So we already figured out with these guys here, a5, a8, a11, a 14, those are going to be 0. It's these ones here that are going to be difficult. So now we're going to continue on this one, and we're going to replace the a6 with what we see here. Look at that. And so now I'm going to have a 2 to the third on the top, and on the bottom I'm going to have 9, 8, 6, 5, 3, 2. And that is annoying, but let's write it down. It would be great if there was a 7 there and a 4 there, because then we can write 9 factorial, but we can't do that at this point. Let's go ahead and replace the a7 with this part right here. So I'll have a 2 to the third on the top, an a1, and then 10, 9, 7, 6, 4, 3. Once again, pretty annoying to say that, you know, because you're missing some of the numbers. You're missing every third number, and that is kind of what we have here. So now I'm going to go ahead. I've run out of room on this slide here, so I'm going to go to the next slide and have some of the things that I have written up on the next slide, which would be a8, a9, and a10. Okay, a8 is 0. So a8 kind of represented the subsequence that is 3n plus 2, a sub 3n plus 2. That is going to equal 0. This subsequence here represents the a sub 3n. So this is what I'm going to do, and this is going to be a little tricky, because some of you are like, is there like factorial notation when some of them are missing? And the answer is no. But what I'm going to do is, why can't I just put a 7 there, and a 4 there, and a 1 there? And you might be thinking to yourself, well, I don't want Vasta doing my taxes, because you're going to mess it all up. Well, if I put a 7 here, and a 4 there, and a 1 there, I have to put a 7 up here, a 4 up here, and a 1 up here. So that's what I'm going to do, and I'll do it in red. And so that makes me happy, because on the bottom, you're like, wow, that makes you happy, Joe? Huh, you're a weird guy. But yes, on the bottom, I have a 9 factorial. And on the top, I have the same thing. Yes, I still have this awkward 1, 4, 7, but that's going to be maybe good enough. So we have to think to ourselves, and you might have to write out a few more of these terms. Maybe you would have to write out a sub 12 to fully get what's happening. But look what's happening here. This 9, you see a 9 factorial on the bottom. Okay, so this 9 is really a 3n, okay, because this is 3n plus 2, so we have a 3n. So this is parenthesis 3n factorial on the bottom. And then you have a 2 to the n power, because n is 3 in this case. Now you're saying, I thought n was like, what did we're going to have to disregard those old n values. I thought n was 7. Just ignore the fact that we had 7 plugged in to get this. N is 3, because this is 3 times 3. So you have a 2 to the 3 on the top, and then you have a 1, a 4, a 7, and then the a naught. So this looks like it goes to 2 below, like 7 is 2 below 9, so this looks like it goes to a 3n minus 2, because this is 3n. So this is me trying to figure out the pattern, so I can rewrite this, and that's what I'm going to do now. Rewrite this so it says 2 to the n, 1, 4, 7, dot, 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 3n minus 2. That's what the 7 is, and you can put a 3 in for n and see that's what you get. You get up to 7, and then you have an a naught 3n factorial. So that is the formula. So this is the most difficult part of these problems, is finding the patterns. Now I'm going to do the same thing on this one, and maybe you can pause the video and see if you can finish off writing a formula that says not a to the 3, a sub 3n, but a sub 3n plus 1. That's what I'm going to write right here. So pause the video and see if you can do it. If not, if you don't want to pause the video, let's go ahead and do this. I'm going to go ahead and multiply 8 on the top and bottom, multiply 5 on the top and bottom, multiply 2 on the top and bottom. So that's what I have, and you're like, where did that 1 come from? I can put a 1 there if I want. And so, on the bottom, I have a 10 factorial. And so look at this. This 10, there's a 10 there. And then we have, this is really 3n plus 1, or 3 times 3 plus 1, so the n goes there, 2 to the n, or 2 to the 3 in this example, A1 is going to go there. This is the tricky part. 2, 5, 8. 8 is 2 less than 10. And so this 10 is really going to be a 3n plus 1. So this might be 3n. This goes up to 3n minus 1. That's what I'm going to write there. And you can go back and check by putting 3 into this formula. And then you end up getting 9 plus 1, which is 10, which you got, and then verifying that this is correct. Okay, now if you were still kind of like, whoa, man, I think I got lost on A9 and A10, then I would ask you to maybe on a piece of paper write out A11, which would actually be pretty simple to see, A12, which is going to kind of line up with this, and A13, which would line up with this. And in these cases, n would then be 4. And then see, write out some and go, oh, I see how you can get that pattern. This is a big disadvantage of not being here, being with you guys in class. This one is a little tricky because you're looking for patterns. I'm going to take the things that are boxed and put them on the next page. That was the hard part about this problem. So there they are. A sub 3n is in blue, a sub 3n plus 1 is in red, and a sub 3n plus 2 is in black. That's 0. My solution for this differential equation is that. Now, just like I broke it up into evens and odds, I'm going to have to break these up into, we don't have words like treven and trod, or, we have to break them into 3n plus 1, 3n plus 2, and that's what I'm going to do. And so I've kind of colored the ones to match the formulas up there. And so you'll see I'm going to replace the a sub 3n with the blue, and the a sub 3n plus 1 with the red, and the a sub 3n plus 2 with the black, with the 0 really. So this is what it's going to look like. Well, let's take care of the 0 one first. So that one's going to get zeroed out. We're not going to write that one next time. And now let me just write out these two terms because it's going to take up some space. There it is. So what did I do going from here to here? Why did I hesitate? Because my formula started at 1, and I didn't really mention that I was going to do this, so I had to actually write out the first term here. N equals 0 is a sub 0, x to the 0, so there was an a naught. And then when I put a 0 in here, I have an a sub 1, x to the 0 plus 1. So I had to take those terms out before I can apply these formulas, because these formulas only apply starting at 1. And so then once I had n equals 1, I went ahead and replaced those formulas. Okay, wow, I think we're going to have to take this to another page. I think we're going to our last slide now. Our last slide, I'm going to rewrite this last line without the colors. I know some people are sad about that. And there we have, yeah, that's, just checking to make sure that's correct. Okay, so we have it without the colors, and I want to factor out, okay, well I'm just going to call those things on the top, I'm going to call those two terms, even though it's more than two terms, but each of those two terms have an a naught in common, so I'm going to factor out an a naught. And then the two terms down here have an a1 in common, so I'm going to factor out the a1, and this is what it's going to look like. It's going to look like this, a naught times this, plus a1 times this. And so here's my original differential equation. We have just solved the original differential equation. It has this solution right here. Now, think about what just happened. This was second order. It didn't have constant coefficients, but it's a still second order homogeneous differential equation. Now, there's a derivative operator. There's an operator notation that I can use, which is d squared minus 2x. And we have just found the kernel of that linear transformation, d squared minus 2x, if you're interested in the linear algebra aspect behind it. And so our solution really looks like this. A naught y1, where y1 is this vector, plus a1 y2, where y2 is this vector. And each of these vectors, y1 and y2, belong in the kernel of some linear transformation, and they get mapped to the 0 vector. And that's kind of what, I mean, there's the linear algebra end of this. So we have this differential equation, y double prime plus minus 2xy equals 0. We have differential equations. We have these things in front of the y double prime, y prime. There's no y prime here, but you have some functions like negative 2x. These are called analytic at x equals a if they can both be written, or if they can be written as convergent power series centered at x equals a with a non-zero radius of convergence. So some of you are like, say, what? You don't have to write this down or anything. So then a would be called an ordinary point of the differential equation, if that's the case. In our differential equations, a equals 0 was ordinary, and if a is not an ordinary point, then it's called a singular point. So we just did series solutions about an ordinary point. This chapter is pretty big, so it has other sections where they talk about solving differential equations on a singular point. So once again, this kind of problem, I will give you guys the take-home problem, which you should worry about after exam 4. So exam 4 will come, and then you'll do that, and then the take-home problem will be counted as points on exam 5. It will just be its own little take-home quiz or whatever, and I'll give you like a week or so to crank out the problem, and maybe doing some of the homework problems will help you crank out the solution. I'll be looking at all the steps, and that's how you'll get your credit. So we don't have to talk about series solutions about an ordinary point anymore in this class. We are off to the Laplace Transform, and I believe I've already done a lecture on that. So you guys have a good day.